let's go ahead and get started. So I hope everybody had a good break, but we're going to get going again with our discussions of rotational kinematics and rotational motion that we left off with last week. Now, just to remind you of some of the equations that we had to discuss rotational kinematics, a whole bunch of them are really basically the same equations that we had for regular kinematics. So to remind you of the one-dimensional kinematic equations that we had one equation that told us what the position was as a function of time for some object, and this said that this was going to be equal to the initial position. I can label as x naught plus the initial velocity times time plus 1/2 the acceleration times time squared. The velocity was given by v as a function of time is equal to v naught plus at. And so these two equations describe the motion of an object that moved in one dimension. So if we had some block and it was moving along some path like this, if we knew what the initial position, initial velocity, and the acceleration of this object were, we could describe its motion with these two equations. Now, when it comes to rotational motion, we have two equations that are essentially the same thing as these equations. And that says that the angle as a function of time, theta of t, is going to be equal to theta 0 plus omega 0 t plus 1/2 alpha t squared. And omega of t is going to be equal to omega 0 plus alpha times t. Okay, now when we compare these equations, we see that the position is analogous to the angle, so there's some comparison between x and theta. We see something similar for the linear velocity v0 and the angular velocity omega. There's really v and omega. And the acceleration, so we had our linear acceleration and our angular acceleration. And so what these two equations describe is the motion of some object that's going around the arc of a circle. So if we had some circle like this, or some arc of a circle, then we could say that the angle as a function of time for this object, if it started here and it's going around this arc of a circle, is given by the first equation. The angular velocity is given by the second equation. And we can even go so far as to say, well, we can figure out what the translation of this is along the arc of the circle, or figure out what the distance is covered across the arc of the circle, if we say that the position is really, or the distance, we could call this some length L, is given by the radius times the angle. So if this is the radius r, we want to know how far along this arc we've gone, and then we can say that this length is going to be equal to the radius times the angle. We could say that the tangential velocity, say that's some v sub t, is going to be equal to r times the angular velocity. And then we could also say the tangential acceleration, a sub t, is going to be equal to r times alpha. Okay, so that's how we can kind of convert between these angular parameters and these linear parameters that are tangent to the circle. Now, in addition to these kinematic equations, we also discussed what the centripetal acceleration of an object is. So we saw from Newton's first law that an object in motion will stay in motion unless acted upon by an external force. And so that means that there has to be some force acting on this object if it's going to go around the arc of the circle. If there's some force, then there's some acceleration due to Newton's second law. And so when you're going around the arc of the circle, there has to be some acceleration that we found was pointing towards the center of the circle. And that acceleration is given by a sub c is going to be equal to v squared over r, where v is the tangential velocity going around the arc of the circle, and r is the radius of the circle. Okay, so any questions about this? This is just kind of an overview of the equations that we laid out last week. Okay. So what we're going to do now that we have these equations, yeah.
Is tangential velocity the same as linear velocity?
It's the same as linear velocity that's tangent to the circle. So to explain that a little bit more, the tangential velocity dimensionally is like a linear velocity. It's a meter per second. Okay, but that's what is my meter per second tangent to the circle? And so this is, it's not linear in the sense that it doesn't go in a line, okay? But imagine I had something and I'm swinging on a string and I cut the string. Then it would go off in that direction. So in that way it is kind of akin to a linear velocity, but the real difference between the velocities that we talk about here is the angular velocity and the tangential velocity. Angular velocity is units of radians per second. So that's what is the angular change per second versus the tangential velocity, which is in a sense a linear velocity. It's a meter per second.
Just because it has the same unit.
Yes, yes. Okay. Other questions? Okay. Good catch. Okay. So let's move into our questions for the day. So this first question says, a ball moves counterclockwise in a circular track of radius r with some constant speed. How far has the ball traveled when it goes from point A to point B? Okay. So go ahead and talk about this one, and then we'll discuss it as a group afterwards. Okay, so let's talk about this one. It seems like I need to ask harder questions. So this one we see that to go from A to B is going to be a quarter of the circle. And we know that a circle has a circumference of 2 pi r. It has a length of 2 pi r, essentially. And so if we wanted to figure out what the length is from A to B, or the distance from A to B along the arc of this circle, this is just a quarter of that. And so that says that this is going to be pi r divided by 2. Okay, so let's look at another one. Okay, so now this one says, similar situation, ball moves from counterclockwise in a circular track of radius r. If the ball starts at rest at point A, what is the average angular speed of the ball if it takes 2 seconds to get to point C? So go ahead and talk about this one. Laura, do this one.
I think she also did this one
last time. Okay.
But you did some.
Yeah.
That she didn't.
Yeah, I think I'm just doing a different order. That's fine. Where'd she finish?
Calculating the acceleration, something that's speeding up and moving faster.
Okay. Okay. I don't know if I have any calculations like that, but I had some concept questions. So. Okay. Good. Good. Okay. Let's back over here. Start over here today. You good? All right. So what are we thinking, guys? What are we thinking?
So we start, we go half the circle. So there's, rather than instead of being fourth place, it's 2. So it's being pi r, the distance. And we do it in 2 seconds, though, so the pi r like 2.
Yeah, that's the arc length we got to go over, yeah.
Just kidding. We can't do it.
Yeah, well that's good though. You look at it and you say, well, I can't do that. So yeah, that's an important thing to realize.
Distance 1, velocity 1.
Well, it's not quite like that either. So think about it like this. So you know how far you have to go, and you could think about this instead of having it going around the arc of a circle. What if I just took that and I stretched it out, and that was just the distance I had to cover, right? So then the question is, how long does it take to cover that distance, or what speed do I need to cover that distance if I want to do that in 2 seconds?
So we want to go distance equals rate times time, dirt.
Say it one more time.
Distance equals rate times time.
Exactly.
Dirt.
Exactly.
So we want to go pi r over 2 equals some velocity in 2 seconds. So what are the units for this? What is that? So what is rad per second?
Rad per second is an angle per second. So the way that you're doing this, and this is good, this is going to give you the tangential velocity. But what we actually want is the angular velocity. So in order to get the angular velocity out of the tangential velocity, we could look at this equation that we have here. So this equation relates the tangential velocity to the angular velocity. So what you're kind of solving for is this, but what we want is that. So then, one more time? Yeah, you could do that. Or, I mean, honestly, you could jump straight to calculating the angular velocity. But there's something you notice, you have something extra in your equation that's not in any of the answer choices, right? You have factor of r. Yeah. So what we need to do is we need to just divide out that r to get it in terms of an angular velocity instead of a tangential velocity. What's up? Well, so what you're kind of calculating and what you're saying is, I'm saying that the distance d is equal to the velocity times time, right? That's what you're doing. And this will give you what the velocity is. So v is equal to d divided by t, which is good. You can do this. But v is not actually what we want. We want omega. And so once we have v, to find omega, we just divide by r. And that's it. Okay. Yeah. All right. Good. All right. How are we doing, guys?
Well, okay, so first we have to give a ring. Yeah, that's
So
that's all we're going.
So the important thing here is it doesn't say speed, and we're going to try to be more explicit now that we have two types of speed. It doesn't say tangential speed, it says angular speed.
So that doesn't include r.
Yes. So
Just 2 pi is the circumference. Divided by 2, divided by 2 seconds.
Right.
Is pi.
well, the circumference is still 2 pi r, but what you're really kind of interested in is what's the total angle of the circle. Total angle of the circle is just 2 pi.
2 pi.
Yeah.
Angular.
Yeah.
Angular.
Because circumference it's a measure of length, right? And what we're really interested in how big is the angle that goes around the whole circle.
I'm going to rewrite this as pi.
Yeah, but I think you got it though. Okay, how are we doing, guys?
Yeah.
Questions?
See, to cancel 1/2 of 2 pi r. Yeah, so it's 1.
Okay, I think you guys are getting it. Questions? Okay, so talk me through what you're thinking so far.
So we need to find the angular speed, so that's the w. So can we use the VT/RW equation?
And one more time.
The VT/RW, can we use that equation?
Yeah, you could use that. Yeah. So then from that equation, what could we find in order to solve for omega? Sure. We know the radius, right? That's kind of a given. We would need to know what VT is then, right? How could we find what VT is? Sure. Distance is equal to velocity times time. Right? So then we're kind of at another place that we have to figure out what some of those things are. Well, we actually know what time is, right? Time's just 2 seconds. So then we need to know what the distance is. So how can we find the distance? Say again?
Pi.
Close. The distance is going to be pi r. The angle that you go over is pi. But if we want to do this in terms of the distance, you say the distance is, well, it's half the circumference of the circle, right? So just pi r. Okay. And then you can kind of connect all the pieces together, and that's pretty much it. Okay. Good. I've been... so let's go ahead and talk about this one. So there's kind of two ways that you can look at this one. And we'll see that they're ultimately the same thing. Now, when we're looking at this, we can start by drawing it. So we have this arc of a circle. Okay, so we could say that the total arc length of this is going to be half the circumference of a circle. So we could say that this L is going to be equal to pi times r, right? Because the whole thing, if I went around the whole circle, that's 2 pi r, but we have half of it. So this is going to be pi r. And we know that we want to cover this distance in 2 seconds. And so we can figure out what the tangential velocity is going to be here, because we know that this L should be equal to v times t. And so we can put a subscript on here so we can solve for the tangential velocity. So we can divide both sides by t, and so that says vt is going to be equal to pi r divided by t. And if we want our angular velocity, we also know that the angular velocity is related to this because vt is equal to r omega. So this is equal to r omega. And then we can see we can solve for omega by just dividing both sides by r. And so that says that omega is going to be equal to pi over t, which is going to be equal to pi divided by 2. Now, another way that we could have come to the same conclusion, we don't even really need to worry about the tangential velocity. If we just think about the fact that we're going over some angle, and it takes a certain amount of time to do that. So what is the angle that we have to go over here? Well, this is just pi, right? So the angle we go over is pi. The time it takes to go over that angle is 2 seconds. And so we can jump straight to what the angular velocity is by saying we have the total angle. That's going to be pi, and we divide by 2 seconds. Okay? Any questions? All right, so let's move on to the next one. All right, so now what we're asked is, this one says a ball moves around moves counterclockwise in a circular track of radius r. What is the average angular speed with an average angular speed of 5 revolutions per minute? What is the angular speed of the ball in SI units? That is, what is it in radians per second? And what is the linear speed of the ball if the radius is 50 centimeters? So go ahead and take a look at this one, and we'll talk about it. All right, so let's talk about this one. So we're given that this object has an angular velocity of 50 revolutions per minute, and what we'd like to do is we'd like to write this in SI, and so that means to convert it to actually 5 RPM is more of a period, but we want to convert this to an angular velocity. And so in order to do that, what we can do is we can say that in 1 revolution there are 2 pi radians, so we have 2 pi radians in 1 revolution, and in 1 minute there are 60 seconds. So in 1 minute there's 60 seconds, and so when we do this, we end up finding that this is going to give us an answer of pi over 6 radians per second. And so then what we want to do is we want to find what this is in terms of a linear speed. And so in order to do that, what we want to do is we want to say that Vt is equal to r omega, which is going to be equal to 0.5 meters times pi over 6 radians per second. And so this ends up giving us an answer of pi over 12 meters per second. Okay, squeaky. Okay, any questions about this one? Okay, so moving on then. Okay, so now this is coming back into our discussion of acceleration when it comes to circular motion. And so what this question says is a particle moves counterclockwise in a circle with a constant speed. Which arrow best represents the direction of the net acceleration of the particle? So go ahead and talk about this one. Okay, so let's talk about this one. So what were some of the ideas that we came up with? How about somebody from over here? What do you guys think? What do you think? A? Why A?
Because it's a constant speed.
Yeah, so this is an object that's undergoing circular motion, and it's also moving at a constant speed. And so because of those two things, the net acceleration is going to be pointed towards the center of the circle. In this case, when we're at this point, that's going to be pointing to the left, which is what A says. Okay, so let's move on to another one. So now, this one says a particle speeds up, moving in the counterclockwise direction in a circle. Which arrow best represents the direction of the net acceleration of the particle? So think about this one now. Okay, so let's talk about this one. I think we mostly have it already. So if we think about what was going on in the last question, this had some acceleration that was pointed towards the center of the circle. Well, this one also has a component of the acceleration pointed towards the center of the circle, but it also has a component of the acceleration that's tangent to the circle. So in addition to having some acceleration pointing towards the center, it has some acceleration that's pointing tangent to the circle. And if we want to find what the net acceleration of this is just some vector addition, right? So we can add these two vectors together, which is like taking this one and then moving it over here, and then drawing the line that goes from the point here to the tip of the second vector. And this corresponds to answer choice B, okay? All right. So moving right along, we have another one here. Now this is a calculation. So this one says a tire of 0.5 meters in radius rotates at a constant rate of 200 revolutions per minute. Find the speed and acceleration of a small stone lodged in the tread of the tire on its outer edge. Okay, so go ahead and talk about this one. Okay, so let's go ahead and talk about this one. So for this question, we're told that this wheel has some radius of half a meter, and that it's rotating at 200 revolutions per minute, which actually happens to be really fast for something that size. So we want to find what the tangential velocity of this wheel is going to be. And so in order to do that, we want to take this revolutions per minute and convert it to a radian per second. And so in order to do that, we can multiply this by 2 pi radians per revolution, and then multiply this by, in 1 minute, there are 60 seconds. And so when we do this, we end up finding that this is about 1 over 10 times 200, which is going to be roughly 20 radians per second. And so then what we want to do is we want to find what the tangential velocity is from this angular velocity. And so in order to do that, we say v sub t is going to be equal to r times omega. We take this and we multiply it by the radius, and we end up finding that this is approximately equal to 10 meters per second. Okay. Now, in order to find what the acceleration is, you really do have two components to the acceleration. Yeah, question?
What happened to the pi?
You just approximated.
I said that this was about 6, right? Pi is 3, 2 times 3 is 6, and I cancel it, that's the 1/10, yeah. Okay, so we know that we have this velocity of 10 meters per second going around the arc of the circle, and what we want to do is we want to find what the acceleration of this is. Now, in principle, this can have two terms for the acceleration. One is the tangential portion of the acceleration. This tells us that this is r times alpha, and the other term comes from the centripetal acceleration. This is the v squared over r. Now, when we look at this, we actually see that this term here is going to be 0 because the angular velocity is constant. So if the angular velocity is constant, that means the angular acceleration is 0. So the tangential term of the acceleration is 0. So we only have to look at the centripetal acceleration here. And so in order to find what the the total acceleration is, we can just take this 10 meters per second and plug this in here. This is going to be AC is going to be equal to 10 squared divided by 0.5. This is going to be 100 divided by half, which is going to be approximately equal to 200 meters per second squared. Okay. Well, it's exactly, but what you would find if you actually plug this in the calculator is something that's very close to 200. It's 219, it looks like. Okay. Any questions about this? Okay, so moving right along then. So we have another clicker question here. This one says, we have this track that a car is going around, and what we want to do is we want to think about where is the acceleration going to be the greatest, okay? Assuming that it's moving at some constant speed tangent to this circle, okay? So go ahead and talk about that one, and then we'll discuss it in the group. So looking at this one, we want to determine where the car has the largest acceleration. So in order to determine where the car has the largest acceleration, what we want to take in consideration is what is the radius of the turn the car is going around here. Because we have an equation that tells us what the relationship between the radius and the acceleration is. And so we see that AC is going to be v squared over r. And so the smaller the radius, the larger acceleration. And so what that tells us is that the answer here should be C. Okay. Moving along then. All right, so this is an open-ended question. It says clicker question at the top, but it's actually an open-ended question. And so this says an automobile whose speed is increasing at a rate of 0.6 meters per second squared travels along a circular road of radius 20 meters. What is the instantaneous speed of the automobile when the instantaneous speed of the automobile is 4 meters per second? Find the tangential acceleration component, the centripetal acceleration component, and the magnitude and direction of the total acceleration. Okay, so go ahead and talk about that one. All right, so let's go ahead and talk about this one. So for this problem, we're told that we have an automobile whose speed is increasing at a rate of 0.6 meters per second squared, traveling along the arc of a circle of radius 20 meters. This has some instantaneous speed of 4 meters per second, and we want to find what the tangential acceleration is, what the centripetal acceleration is, and what the magnitude and direction of the total acceleration is. So in order to do this, I'm going to start by just drawing the arc of a circle so we can see in a picture kind of what's going on here. So I'm going to say that this is going around this direction, and this is going to represent the tangential acceleration. And we're actually told what the tangential acceleration is here. This is just going to be the 0.6 meters per, how are we doing this? We're doing this in terms of meters per second. So this is 0.6 meters per second squared, okay? Now, in order to find what the centripetal acceleration is, so this is going to be a tangential acceleration, a sub t. The centripetal acceleration, a sub c, is going to be equal to v squared over r. Well, we're told that v is going to be 4 meters per second, and so this is going to be 16 meters per second quantity squared, divided by the radius, which is a radius of 20 meters. So this is 20 meters. And so this is going to give us an answer of 0.8 meters per second squared, okay? So this 0.8 is representing this portion right here. Now, if we take these two arrows that I have here, we can form some triangle. And so we can form this triangle that looks like this. So this is going to be, and let me draw this a little bit more to scale. So this looks a little bit more like that. Okay, so this is going to be 0.8 meters per second squared. This is going to be 0.6 meters per second squared. And in order to find what the total acceleration is, we can use the Pythagorean theorem. And this ends up being a very nice number. This is going to be 1 meter per second squared. Now, something that you'll notice about this is that this is kind of what's called a Pythagorean triplet. And a Pythagorean triplet is a set of numbers that satisfy the Pythagorean theorem such that each one of the numbers is a whole number. And so to see why that's true here, what we can do is we can kind of manipulate this in order to get it to really look like a Pythagorean triplet. So if we multiply each one of these numbers by 10, that gives me 10, this gives me 8, this gives me 6. We could divide these by 2 as well, because if I scale all of these at the same time, I'm still working with similar triangles, right? So if I divide these by 2 now, this makes this 5, this makes this 4, this makes this 3. So this is actually a 3, 4, 5 triangle. It's just maybe a little bit difficult to recognize because it's been stretched a little bit or compressed. But this is the triangle that we have here, and if you're familiar with these types of triangles, you know then that this angle right here is going to be 53 degrees. This angle right here is 37 degrees. And so that gives us all the, in conjunction with the picture that we have here, that gives us all the directional information that we need. Yeah?
In the exam, should we say in like degrees or in radians?
For these ones, probably in degrees, but if I had my way, everything would be in radians, right? As long as you label what it is, right? If you do this in radians, say that it's radians. If you do it in degrees, say that it's degrees. Any other one is correct. Okay, yeah?
Do we have to indicate the direction?
You have to indicate the direction. Yeah, so I mean, what I kind of did here was I indicated the direction by drawing the triangle and representing the direction of the vectors here. But that's what this is really, right? Because that's the whole thing, because I drew the vector signs in there now.
To say like if you
Yeah, we could say 53 degrees west of north. Yeah. Okay. Now these kinds of triangles are, if you end up taking the MCAT, LSAT doesn't have math, I don't think, but the MCAT has some math component to it. If you're familiar with these kinds of triangles, they like to use these triangles a lot. And it can save you a lot of time on the calculations that you have to do. If you're familiar with them already, then you don't have to plug things into your calculator. You can just look at it and be like, okay, well, I know this type of triangle before I've seen it. Okay? Any questions about this? Okay, so moving on. All right, so the next question says, ladybug sits on the outer edge of a merry-go-round and a gentleman bug sits halfway between her and the axis of rotation. The merry-go-round makes a complete revolution once each second. We want to compare the gentleman bug and the ladybug's angular speed. So how are these related to each other? Take a look at it and talk to each other to try to figure out the answer. Okay? Okay, so let's look at this one. So this one's kind of important because there's a little bit of a misconception that people have, and it has to do with which velocity we're looking at. Now this one says it says very explicitly that we're talking about the angular velocity, not the tangential velocity. So if we think about this in terms of the tangential velocity, obviously the bug on the outside has to go around faster than the bug on the inside if they're on the same radial length from the center, and they maintain that. So we can say that the tangential velocity is going to be larger for the outer bug, but the angular velocity is actually the same, because if we think about this, these are constrained to move along the same line, say, like that goes through from the center of the circle to the outside, and so they're always on this same line. And if this goes around by some angle here in a certain amount of time, they're covering the same angle, right? And that's really what the angular velocity is telling us. It's how quickly we go around to cover some angle. And so the angular velocity is independent of the radius here. It's the tangential velocity which is not. Okay. All right. So let's move on to the next one. Okay. So this one, now this one's getting a little bit more complicated because the things that we've done so far have been for constant angular velocity, or we were talking about some instantaneous situation when we had some angular acceleration. This one actually wants us to determine something about the angular acceleration. So go ahead and talk about this one, and then we'll talk about it as a group afterwards. Okay, so let's go ahead and talk about this one. So in order to solve this problem, we need to find what alpha is. That's really what we're asked here. But the problem is we're not told what the initial angular velocity is. And so ultimately what we need to do is we need to set up a system of equations in order to solve for what alpha is. So the things that we do know are what t is. So t we're given, this is going to be 3 seconds. In some sense, we know what theta of t is, or what the final angle is going to be, because we know that this is going to be 37 revolutions, okay? So because we know this is 37 revolutions, we know that theta is going to be equal to 2 pi radians per 1 revolution times 37 revolutions, okay? Now, we also know what the final angular velocity is. This is given as 98 meters or radians per second, so this is going to be omega f is going to be equal to 98 radians per second. Now, what we can do is we can take these two equations here and then eliminate what omega naught is, and then evaluate the other equation for alpha. Okay, so in order to do that, the first thing I can notice is I can take this omega 0, I can say this is 0. Okay, that's going to make our life a little bit easier. So then what we can do is I can, let's give these some different indices rather than saying it's some function. Let's say this is theta f and omega f. And then we can take the second equation and solve for omega naught. So when we do that, we see that omega naught is going to be equal to alpha t, this is going to be omega f minus alpha t. We can take this and we can plug it into this equation, and so then we see that theta f is going to be equal to omega f minus alpha t times t plus 1/2 alpha t squared. So we expand this and we end up finding that this is going to be 1/2 minus 1, which gives us a negative 1/2, and so this is going to be omega f minus 1/2 alpha t squared is equal to theta f. We lost a t here. Move this to the other side, move that to the other side. Let's leave this stuff here for the time being. This is going to be 1/2 alpha t squared is going to be equal to omega f t minus theta f. Multiply both sides by 1/2 over t squared. We end up seeing then that this is going to be equal to 2 over t squared times omega f t minus theta f. And then when we plug this in and put our numbers into this equation, we end up seeing that this is about 13.7 radians per second squared. Okay. So the algebra was a little bit messy, and to be perfectly honest, any question that we ask on the exam would not have algebra this messy. But the important thing to take away from this is the fact that we can read the question and realize what information we have and what information we don't have, and what it is that we need to solve for. And the rest of it is really just the algebra in order to evaluate it. Okay? Any questions about this one? Okay, so moving on to the next one. Okay, so this is getting more into some of the things that we talked about last time, and this has to do with forces when we're talking about centripetal acceleration. And so this question says, a rider in a barrel of fun ride finds herself stuck with her back to the wall. Which diagram correctly shows the forces acting on her? Okay, so this is spinning around, and that's what's keeping her from sliding down. And so what we want to do is we want to pick which one of these best represents the forces that are acting on her. So go ahead and talk about this one, and then we'll talk about it together afterwards. So let's go ahead and talk about this one. So there's a couple of these that we could almost eliminate right away because of what we know what needs to happen in the y direction, right? Because we know she's not going to be moving up or down, so the sum of the forces in the y direction should be 0. So any one of these that doesn't have x and or the two y components canceling can't be true. But we also know something about the direction the acceleration should point based on our discussions of centripetal acceleration before, and that's anytime that something's going around in a circle, the acceleration has to point towards the center of the circle. And so if the acceleration has to point towards the center of the circle, the force also needs to point towards the center of the circle from Newton's second law. So remember Newton's second law, this one never really goes away, right? So the sum of the forces is equal to the mass times the acceleration. So if I sum my forces in the radial direction, it needs to point towards the center of the circle. And so when we look at that, we see that the only choice that works for is going to be answer choice 1. And so the only force acting on this is really the normal force that's pointing towards the center of the circle. Okay? Any questions about this one? Okay. Yes. Yes.
So the force of the barrel turning makes it so she doesn't fall?
Well, it's really more of a force of friction, because what's happening here is the force pointing out is a normal force. We have a normal force. There's a force of friction. So she has gravitational force acting on her. She also has a force of friction opposing that due to the normal force of the barrel acting on her.
How did you not just like die? Because they must go fast enough.
Well, sure. So, I mean, I couldn't tell you for the numbers how fast this would have to spin for somebody with a certain mass. There are rides like this at amusement parks that don't kill people. So it's not like this has to spin at like 20,000 RPM in order for it to like stay stuck to the wall. This is more like maybe 2 or 3, more than 2 or 3 revolutions per minute. Maybe like 10 revolutions per minute. So something, it's not super fast, but it's something that can happen. If you go to like these sketchy carnivals that they have that move around town to town, they have these kinds of things. Okay. All right. I saw one in Texas once actually when I went to one of those carnivals. Okay. So that's actually I'm going to call it for today. So we're going to pick up again where we left off on Thursday.